How can you convert rational numbers into decimals? Again, we're going to use long division. That's the key. To divide the numerator by the denominator. If the decimal terminates or repeats, then you have a rational number. If the decimal continues forever, then you have an irrational number, that new class. Let's remind ourselves how to use the long division. Let's look at our example. 7 over 33. We can change to 7 divided by 33. A reminder of long division, you keep trying to see 33 going into first 70, then 40, 70, then 40, and we can see it will keep trying to go into 70, then 40, 70, then 40, giving us a repeating decimal of 0.21 repeating. Fractions as repeating decimals. A rational number is a number that can be written as the ratio of an integer with a natural number. The decimal expansion of a rational number will always repeat, provided we allow zeros to repeat. For instance, a common fraction, a common rational number, 1 over 4, is equal to 0.2500000, and another common rational number, 1/3, is equal to 0.3333333. We have repetition. To save time, though, we typically let 1/4 equal 0.25. That's then called a terminating decimal, since all those repeating zeros are unnecessary. But when you have a repeating decimal, it's typically written using a bar line. The bar line appears over the digits that repeat. So here's some examples. Instead of 1/3 being 0.3333333 forever and ever, repeating, we can say it's 0.3 repeated, and the bar over the 3 intends that that's just the digit repeating. 0.12 repeating is the 1, 2 is repeating, so 0.12, 1, 2, 1, 2, 1, 2, 1, 2. 1.83 repeated is just the 3 repeating, so 1.8, 3, 3, 3, 3, 3, 3, 3. Now, all rational numbers a over b can be written as non-terminating decimals. And we can check this on a calculator, all of these examples, or grind through some long division. Instead of 1/4, you would think it's 1 divided by 4, 2 divided by 3. But each time, whether the calculator is doing the division or you are by hand, you are going to get these results. Now, in the left column, we see that only one digit repeats. The bar line is only over one number in each answer. In the right column, though, the examples vary and repeat every 2, 3, or even in the last one, 2 over 7 is 7 digits. So we can create any pattern of repetition we want in creating a non-terminating and repeating decimal. And every one of them can be expressed as the ratio of an integer to a natural number. Now we can demonstrate this back and forth. As many times as we want with any rational number, but let's see a couple examples, starting with the repeating decimal 0.666666. Let's see how that can be written as a over b, the ratio of an integer and a natural number. So let x equal 0.6 repeating, which is saying that x is equal to 0.6666666666. Now, let's notice what happens when we multiply a one-digit repeating decimal, which this is, by 10. So 0.666666 times 10 is 6.666666. The decimal point slides one space to the right, and the new number looks similar to the original number. So now we have 10x equals 6.666666. So now we're going to subtract that x, that repeated part, from both sides. If we want that rational or that ratio, that rational number as a ratio, we need to get rid of the repeating part. So we need to subtract it from both sides. Subtract x. So now we have that 10x minus x equals 9x. And 6.6666 minus the 66666 minus the repeating part is just the 6. This part cancels out. Now we can solve for x by dividing both sides by 9. So 6 divided by 9. We can simplify or reduce by a factor of 3 to be x equals 2 over 3. So the repeating decimal 0.66666 or 0.6 repeating is also written as the fraction, the ratio of 2 to 3. Now let's see the same process with the number 1.454545. So we're going to demonstrate, we're going to turn that repeating decimal into a ratio of an integer to a natural number. So let's let x equal 1.45, repeating, where 45 is the repeating part. So we can expand that to be 1.454545. Now let's notice what happens when we multiply that 2-digit repeating decimal by 100. Well, we can see that the decimal point slides 2 spaces to the right, and the new number looks very similar to the original number. So we have 100x equals 145.454545, but we need to get rid of that repeating part. So we're going to subtract x from the left, which is the same as 1.454545 from the right. So that's going to give us 99x equals 144. So now if we solve for x, we'll divide both sides by 99 to have x equals 144 over 99, which reduces by a factor of 9 as 16 over 11. So the repeating decimal 1.45 repeating can be rewritten as the ratio of 16 over 11. Now let's try to apply what we've learned and try to fill in the blanks. So let's demonstrate that the repeating decimal here, 0.151515 or 15 repeating, can be rewritten as the ratio, or as a ratio of an integer to a natural number. So x equals 0.15 repeating. First they expanded. So then they're going to multiply both sides by 100. So if we multiply the right side by 100, that will give us 15.151515. A very similar repeating decimal. So that same repeating decimal, we have to get rid of the repeating part. So we're going to subtract x from both sides, which is the repeating point part of 0.151515. Not 0.151515, which essentially cancels out the repeating part, leaving with just 15. So 100x minus x is 99x, so 99x equals 15. If we divide both sides by 99, we get 15 over 99, which can reduce by a factor of 3 to be 5 over 33. So 0.15 repeating is the same as the ratio 5 over 33. Let's see what 0.444 or 0.4 repeating can be written as. So if x is 0.4 repeating, we expand it, and then we need to multiply both sides by a factor to get a whole number in the number itself. So it's a 1-digit repeating decimal, so we're going to multiply both sides by 10 to get 4.44444 repeating. So if we have 10x equals 4.4444 repeating, we need to get rid of that repeating part, so we'll subtract x from both sides. So we'll subtract 0.44444 from the right. That'll give us 9x equals 4. And if we divide both sides by 9, we'll have x equals 9 over 4. So that gives us that 0.4 repeating. That repeating decimal is the same as the ratio of 4 over 9. Let's do a couple from scratch. So let's demonstrate or show that the repeating decimal 0.505050 is the same as a ratio of an integer to a natural number. So first, let's let x equal 0.505050, that repeating decimal. Now there's two digits repeating, so we need to multiply both sides of the equation, both sides of the equation by 100. So 100x would equal 50.505050 repeating. So that 100x we need to subtract the repeating part from the decimal, 0.505050. So we'll subtract x and 0.5050 since they are equivalent from both sides to cancel that out to get 99x equals 50. That's what was left when you take away the repeating part of the decimal. If we then want to solve for x, we'll divide both sides by 99. And we'll end up with x equaling to 50 over 99. That is the ratio that is equivalent to 0.50 repeating. One last example, let's write or demonstrate 0.272727 as a fraction. So let's let x equal 0.27 repeating, 2727. Since two digits are repeating, we're going to multiply both sides by 100 to get 27.2727 repeating. Then we need to subtract x from both sides, subtract that repeating part from the right, which will leave us with 99x is equal to 27. Then we need to isolate x, so we'll divide both sides by 99 to get that x equals 27 over 99, which can reduce by a factor of 9 to be 3 over 11. So 0.2727, 0.27 repeating is the same as the fraction 3 over 11. So this process, we can see that those rational numbers can be written as a ratio or a repeating decimal. So after completing several problems that have you trying to demonstrate that repeating decimals are the same as these ratios of integers to natural numbers, you start to notice some patterns. So look over our answers from the last several questions. Did you notice any patterns? Well, if you look closely, there is a pattern that the digits that repeat in the number will become the numerator in the ratio, and the number of digits that repeat will become the number of nines in the denominator. So I can come up with a repeating decimal. Let's say 0.62 repeating. So based on my pattern, without doing any work, the digits that repeat will become the numerator. So 6 and 2 are repeating, so 6 and 2 are my numerator. And the number of digits I have repeating, 2, will become the number of nines in the denominator. So if there's 2 digits, I'm going to have 2 nines, 99. So without doing any work, just based on the pattern, I can see that 0.62 is going to equal to 62 over 99. I can do it again for 0.2 repeating. 0.2 repeating, I'm going to have 2, that number that's repeating, and since it's one digit, it'll be 2 over 9. So 2 nines is the same as 0.2 repeating. So you can use that to your advantage and save you a little bit of time, or a good way to check your answer. Another interesting thing to see is this example. This is a very interesting example trying to convert 0.9 repeating to a fraction. So let's go through our general way. We have x is equal to the expanded form, 0.999. So then, since it's one digit repeating, we're going to multiply by 10, which will then give us 10x equals 9.9999, but we're going to subtract x from both sides. So if we subtract the x, we can think of x being the 0.9999. We need to subtract it to get 9x equals 9, and then if we divide, we get that x equals 1. So this is very interesting because we end up with 0.9 repeating as a repeated fraction is equal to the ratio of 1, or 1 over 1. So this is just because this repeating decimal is going on and on and on forever and ever and ever and ever, that this process is creating the fact that it is so close to 1 that it just equals 1. So it's a little tricky since we know that 0.999 isn't really equal to 1, but based on this process it is. It's just a matter of looking at the number since it's just so close to 1. So, based on this, 0.9 repeating is equal to 1 in this example.